Hi, and welcome to Software Design and Development, Option 2, Lesson 10, Logic Gates. Here are the little stop points. Pause if you'd like to read them. So the first thing we have to talk about with logic gates is Boolean logic, and it was a concept developed by a guy named George Boole. He theorized that all logical inferences could be evaluated as either true or false, and he also thought to apply mathematics to logical thinking, giving us Boolean algebra. In practice, Boolean logic was found to be a perfect match for the way electronics work, and has been an extremely part of all aspects of computing, including computing logic, circuit design, and programming. Logic gates are a concept that demonstrates the operation of a circuit. Think of them like the algorithms of circuit design. Logic gates have a number of inputs and outputs, and letters can be used to represent each of the inputs and outputs. Circuits work using Boolean logic, hence each input or output can be one of only two values, a 0 or a 1. And each logic gate takes one or more inputs and manipulates them in some way to give an output. We can also represent the logic of a gate or circuit using a truth table, and algebraically using Boolean algebra. Both these concepts will be explained as we go, both for each logic gate and as a summary at the end. We'll be doing heaps and heaps of examples, so it's not massively an issue if you don't get it straight away, but through practice it'll definitely become easier. The other thing you need to understand are truth tables, and truth tables are a way to represent all the inputs and outputs of a circuit and their values. Inputs and outputs are represented by letters, except where there is only one output, when the word output could also be used. An example of a truth table is found to the right. You'll see when we do the truth tables that the numbers should be in order in binary. So we've got 0, 0, and then 0, 1. The next number in binary is 1, 0, and then 1, 1. Doing a truth table in this way makes it really easy to tell if we've covered every possible value or not. Boolean logic deals with concepts of true and false. In computing, it is understood that some quantities are equal. True is 1, false is 0, and blank. In Boolean logic, true and 1 are used interchangeably. Similarly, false and 0 are interchangeable. So, moving on to the gates themselves. This is an AND gate, and it has two inputs, input A, input B. It will only output true if both inputs are true. And the Boolean algebra representation of an AND gate is A dot B. In mathematics, the dot can also stand for multiplication or times. So this is kind of saying it's A times B. Okay, and that's the answer there. And if we take A times B, mathematically, we can see that 0 times 0 gives us 0, 0 times 1 gives us 0, 1 times 0 gives us 0, 1 times 1 gives us 1. So that kind of makes sense. Okay, the next one is an OR gate, and it has two inputs. It will output true if one of the inputs are true. And the Boolean algebra representation of an AND gate is A plus B. So, through here we've got input A, input B, and an output. So we can see that 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is in binary 1, 0, but in Boolean algebra, 1 plus 1 is also 1. And so that's the truth table there. This one's a NOT gate, and it has one input, and what it does is it flips the value of the input and turns it into the output. And the algebra representation of this is A with a line on it, or A apostrophe. Okay, so we can see here, we input A, we input 0, we output 1, we input 1, we output 0. Okay, so NOT gates are a really easy way to flip the values over. And this is a NAND gate. It can be constructed using an AND gate and a NOT gate. It flips the output of an AND gate, so only outputs true if both outputs are not 1. And the Boolean algebra representation of a NAND gate is A times B, so that's the AND bit, with the line across the top to signify NOT. So that means not A times B, so not AND. And we've got here A times B in brackets with an apostrophe. So the apostrophe and the line represent the NOT bit of the AND gate, and obviously the dot represents the AND bit of the NAND gate. We've got two inputs here. In the logic gate diagram, we see this dot as well. The dot is the same as the dot on the NOT gate, and that always signifies the fact that it is a NOT version of one of the gates. Okay, and over here we've got the output, which we can see is exactly the opposite of the AND truth table. So this is an OR gate, and it can be constructed using an OR gate and a NOT gate. It flips the output of an OR gate, so outputs are true if only if both outputs are 0. And we can see the Boolean algebra representation of an OR gate. It's A plus B with the line, or A plus B with the apostrophe. Again, the same as the OR gate with the line or the apostrophe to represent the fact that it's the NOT version of it. Inputs are the same. We've got the dot like we had before with the NAND gate, and we've got the truth table here. As you can see, it's only true if both outputs are 0. The last one is an XOR gate, and it's probably the most complicated of the logic gates, and it can be constructed using a combination of AND, OR, and NOT gates. They can also be constructed by solely using NAND gates. An XOR gate, or an exclusively OR gate, only outputs true if one of the inputs is true. If they are both true or false, it outputs false. And the representation of this is the plus in a circle. Okay, so the other difference is with when you actually draw the gate itself, you have this second line, and that represents the fact that it's exclusively OR. So when we go to the truth table, we can see they're both 0, it outputs 0. If one's true, it outputs 1. So 0, 1 is 1, 1, 0 is 1. But if they're both true, it outputs 0 or false.